Good morning. Welcome you all to the Journey of Petroleum Part 5. I am Jairai Nalasambi, Senior Process Design and Technical Safety Consultant at iFluids Engineering. Today we will discuss about hydrogen generation unit, in which we will discuss the plant overview, feed pretreatment, reforming, that is pre-reforming and tubular reforming, CO conversion in ship converter and hydrogen purification in PSA unit. The process steps involved in hydrogen production are feedstock treatment, that is feed hydrogenation, dechlorination and desulfurization. And the pre-reforming, it is optional. Certain hydrogen generation units are having pre-reformer and certain are having only tubular reformer. Then steam reforming, CO conversion in ship converter and hydrogen purification. In the feed pre-treatment section, the hydrogenation is the first reactor in which the reaction takes place is RSH plus hydrogen gives RH and H2S. That is, R is the hydrocarbon radical. It can be CH4 or C2H6, anything it can be. So, SH is the radical of sulfur component. And if you add hydrogen, the sulfur is removed to form H2S, hydrogen sulfide. Thereby, from the hydrocarbon, sulfur compound is removed. The various sulfur components R1, R2, there is more heavier hydrocarbon compound. So, all this can be treated by adding hydrogen under pressure in presence of catalyst and temperature. The temperature here we maintain is 380 degrees centigrade, and the catalyst is COMO or NIMO, that is cobalt molybdenum or nickel molybdenum catalyst bed. Through the bed, the feed vapor, that is naphtha or natural gas, is passing through it. Then chloride removal is the another important thing. For this, we use potassium carbonate as the catalyst. Potassium carbonate reacts with hydrogen chloride and to form potassium chloride and potassium bicarbonate and hydrogen chloride, and again it gives potassium chloride and H2O and CO2. The absorption of sulfur compound, that is the first reaction in COMO bed, that is cobalt and molybdenum bed, the sulfur compound converted into H2S as organic sulfur. Whereas here in the last line, absorption of sulfur compounds in zinc oxide bed is inorganic sulfur, that is hydrogen sulfide, carbonic sulfide, all these are react in presence of zinc oxide with the zinc oxide and to form zinc sulfide and water and CO2. This is the pre-treatment, that is saturation, removal of sulfur, removal of chloride component and removal of inorganic sulfur component. This is the block diagram of the unit, that is hydrocarbon feed is entering along with hydrogen in hydrogenation reactor where we have cobalt molybdenum catalyst, and next one is the chloride removal bed where we have potassium carbonate as the catalyst, and the last one is zinc oxide bed. Here all the inorganic sulfur compounds are removed, and also this act as any slippage of sulfur from the reactors, the previous reactors, that slipped impurities will be caught here so that this will not harm the reformer catalyst. Why we should pre-treat the feedstock? That is very important. Sulfur, chloride, all these components are poisoning the reformer catalyst. Poisoning means inactivating or reducing the activity of the catalyst. So here it is a steam reforming, how it happens. Steam reforming is with a hydrocarbon compound, say let us say is CnHm is the hydrocarbon compound, along with the N molecule of water is added, there is steam, and heat is also added, it gives NCO, carbon monoxide, plus M/2 plus N hydrogen, that is the first reaction. The heavy hydrocarbon compounds are converted into lighter fraction, that is methane CH4. Again it combines with water, that is nothing but steam plus heat gives CO and 3 hydrogen. This CO again combines with the steam, available steam, to form CO2, that is carbon dioxide, and hydrogen, and this reaction is a exothermic reaction, so heat is liberated. The first two reactions are endothermic, so heat is supplied continuously. All hydrocarbon, that is N, if you take the carbon, number of carbon atoms are more than 2 or equal to 2, are completely or irreversibly converted by reaction 1, this reaction. And the second exothermic shift reaction will be close to the equilibrium when it comes out of the reformer section. So, for example, in place of N and M, if you apply the CH4 formula, methane formula, for C instead of N you put 1, instead of M you put 4, then N is 1, so 1 H2O plus heat gives NCO, means 1 molecule of CO, and it is H is 4, the M is 4, so M by 2 is 4 by 2, there is 2, plus N, again it is 1 molecule, so 2 plus 1, 3 hydrogen. So the equation valid for all hydrocarbon, heavy hydrocarbon also. So reaction 1 is strongly endothermic, that means we need to give lot of heat. Design of steam reforming process is dictated by these constraints, that is, normally reforming reaction favors at low pressure and at high temperature, whereas we cannot maintain low pressure because in the PSA unit, that is pressure swing adsorber for purification of hydrogen, it needs certain pressure to, based on the pressure only that unit operates, one point. And another one is the downstream units where we are supplying hydrogen, they also need hydrogen at higher pressure. That's why at the optimum pressure of around 25 to 26 bar is the pressure maintained in the reformer. Reforming reaction is favored at low pressure. Reaction best operated at low pressure. However, there are other considerations, that is PSA operation is 10 to 25 kg, depends upon the capacity, it varies, and bad limit pressure requirement, there is a customer requirement. Customer means a downstream unit. So temperature in the reformer tube is, typical reformer outlet temperature is 800 to 950 degrees Celsius. Higher the temperature, lower the methane slip. That is, methane slip means it's a base stage of feedstock. So we should try to eliminate or avoid the methane slip. Accordingly, the temperature is maintained based on the product temperature, sample analysis. Higher temperature calls for improved metallurgy. That is also very important. When we increase the temperature, the reformer tube metallurgy should withstand the temperature. It should not deform by the heat applied on it. So higher tube wall thickness and increased fuel consumption is also required. Reforming reaction rate is significant above 530 degrees centigrade. However, when we have pre-reformer, this temperature we can go up to 650 degrees centigrade at the inlet of the reformers. Another important factor in steam reforming is steam carbon hydrocarbon ratio. Sufficient steam to avoid carbon laydown on the catalyst. That means if the steam is not sufficient, the feedstock may settle as a coke or carbon on the surface of the catalyst. If it settles on the surface of the catalyst, one is it will plug the pores of the catalyst, that is the active site of the catalyst. Another one is if it lays down on the top surface, it will increase the differential pressure across the tube so that the flow will get restricted. So the typical value for steam carbon ratio is 3 to 3.5. Whereas when we have pre-reformer, the ratio can be reduced to 2.5 to 3. That is the advantage of having pre-reformer. Main advantage is most of the hydrocarbon molecules are converted into lighter fraction, that is to methane. And another one is you can have less steam carbon ratio so that we can conserve a good quantity of steam. And one more thing is you can increase upon the temperature at the reformer inlet, because when we use the heavier hydrocarbon, there is a possibility of cracking. If cracking reaction takes place, then the carbon lay down on the surface of the catalyst is possible. So when it is completely converted into methane, that cracking reaction possibility is very less. So typical reforming reactions are carried out over nickel catalyst. This is a nickel catalyst in a heated tubular reformer. In the tubular reformer, the catalyst is filled inside the tube, and the available void space in between the catalyst particles, the feedstock gas in gaseous state is entering into the passing through it. When it passes through the tubes, the reforming reaction takes place. The capacity of hydrogen units are it is up to 1,30,000 Nm cube of hydrogen can be produced per hour. Even higher than this rate is also available. Furnace box is a box type furnace. That is, a reformer is a box type furnace. Radiant section including a convection section, that is radiant section and convection section also available. The convection section we recover the waste heat from the flue gas. The typical diameter of tube, reformer tubes are 100 to 150 mm diameter, and the length of the tube, vertical length of the tube is 10 to 13 meter length. The inlet temperature varies from 450 to 650. If we have pre-reformer, we can go up to 650, and the outlet temperature to 950 degrees centigrade. Sometime it can go up to 1100 degrees centigrade also. Burners are placed in a variety of ways: side fired, top fired and wall fired burners, to distribute the heat evenly to the reformer tubes. So maximum temperature at this point already we discussed. The reformer tube is designed for the normal operation life of 100,000 hours, that is 1 lakh hours life. And what is the metallurgy for this tube? Very high temperature it should be sent, high rate of feed it should handle without restricting the flow. So for low severity reformers, 25 chromium, 20 nickel is the composition of the metallurgy of the tube. Whereas for high severity, 25 chromium and 35 nickel, as well as some micro alloy also added like niobium, titanium and zirconium, along with the 25 chromium and 35 nickel metallurgy. This gives more strength to the tubes of the reformer. This is the picture of a reformer when it is online. So all this side the light glowing are the burners, online it is in fire. To avoid the direct hitting of flame on the tubes, if the flame hits on the tube, then the impingement of flame will deform the metallurgy as well as it weakens the tube. To avoid that, the flame is travel in this side way along the refractories. The heat is radiated to the tubes, and from the tube wall it is furtherly transferred into the catalyst and the feedstock. The outer structure of the reformer looks like this, like a big building, it is like that. Whereas inside it is the vertical tubes. So the outlet of the reformer, that is this one, this tube outlet will have around 65 to 70% of hydrogen after that reforming reaction. It will contain CO, CO2 and water particles. That is, we add steam into the reaction for steam reforming. Some excess steam always we are allowing. So this excess steam will come as a steam in the, along with the product also. That is, the product is called as synthesis gas. So this we have to purify. For purification, before purification, we have to recover maximum hydrogen. So to maximize the hydrogen product hydrogen, the CO, whatever the CO composition is there in the synthesis gas, that is the outlet of reformer. It is again reacted with the steam to give CO2 and hydrogen. So critical for economics of hydrogen production, this is very critical, because otherwise the CO will go waste. So unconverted CO is a loss potential for hydrogen production. This exothermic reaction is favorable at high steam gas ratio and low temperature unaffected by pressure. So by converting the CO, this is the water gas shift reaction, famously called as water gas shift reaction. The CO plus water gives CO2 and hydrogen. So we convert the possible CO to hydrogen also. After the shift conversion, we have to purify the hydrogen product. See, this is the synthesis gas coming out from the CO shift converter. After shift converter, this is process condensate separator is there. Because we add steam, some condensation will take place after the cooler. So this water should not be allowed, water will not be tolerate in the PSA adsorber unit. The adsorbent will not tolerate moisture. So this water particle should be removed here. So water free synthesis gas is going to PSA unit. These are the PSA adsorbers. These are the PSA adsorbers. So pressure swing adsorptions. See, the adsorption reaction takes place based on the affinity of the gases towards the external surface of the adsorbent. Different gases have different affinity to adsorbents depending on pressure. Using this property to separate gas component in an efficient and continuous basis. Unless it's a continuous basis, we cannot ensure hydrogen production in a continuous basis to the consumers. So the pressure swing adsorption process is the easiest process. It uses very less energy in the sense for operating the valves of the adsorbers only. Some pressurized instrument air is used, otherwise there is no much energy we use. So pressure swing adsorption process has 4 basic steps. One is when you allow the feed gas to the adsorber from the bottom, the adsorption process takes place. That is, the adsorbents absorb all impurities like nitrogen, CO, CO2 and hydrocarbon on the surface. So when it absorbs, only the component or molecule which doesn't get adsorbed on this adsorbent only will come out, that is nothing but our hydrogen. So once this adsorption in a single vessel is over, that means it has collected all the impurities like nitrogen, CO, CO2 and hydrocarbon. So any shaped hydrocarbon, if it is there, that will be also adsorbed. So it will attain the saturation limit. So further feedstock, it will not adsorb any impurity, so that means the impurity will escape along with the product hydrogen. So this we have to regenerate. For regeneration, the feedstock will be automatically switched over to the next adsorber, and this adsorber vessel will be isolated and depressurized automatically. When it depressurized, this adsorbed impurities will desorbed or eliminated from the surface of the adsorbents. We know that adsorption takes place at low temperature and higher pressure. When you depressurize, instead of adsorption, the desorption takes place, that is removal of the impurities. After removing, we have to regenerate the adsorbents. For that, we introduce pure hydrogen into that. This pure hydrogen is coming from the another vessel which is going to depressurization. So the part of the hydrogen, pure hydrogen will come here, and while doing repressurization, only pure hydrogen is used for repressurization. By this, the vessel is getting regenerated and ready for receiving next feedstock. One vessel is on adsorption pressure, next will be on depressurization, and another one may be on regeneration, and one more thing may be in pressurization. That sets of activity will be take place. So when these set of activities are taking place, the hydrogen production is continuously flowing through the product header. So by this way, we can produce hydrogen continuously for the suppliers. Why do we discuss about hydrogen under the topic journey of petroleum? Journey of petroleum, for certain treating of the petroleum products or the in between products, intermediate products, we need hydrogen to treat them. Without hydrogen, a petroleum refinery cannot be run. So, like desulfurization of kerosene, desulfurization of diesel, naphtha, isomerization units, hydrocracker units, all these units consume lot of hydrogen. So, a dedicated hydrogen production unit is required for all the petroleum refinery. So, that's why this hydrogen production is being discussed in the journey of petroleum. So, in the next video, we will meet on another subject. Thank you all.